The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
I wanted to give everybody a more conceptual idea of what Big O notation was, as well as hopefully answer any lingering questions you might have about object-oriented programming. So I have these notes, and I typed them up, and they're pretty detailed. So I'm just going to go through some points kind of quickly. So first up, who's still kind of unclear about why we even do Big O notation? OK. So who can explain why we do Big O notation quickly? What is it? Yeah.
Like an upper bound on how long something's going to take.
Right, exactly. So Big O notation gives us an upper bound on how long something is going to take. Now, something that's important to remember is it's not a time bound. Okay? So something that's often confusing is that people say, oh, this is something that'll tell us how long our program is going to run. That's actually not the case. Big O notation informs us of how many steps something is going to take. And so why is that important? Well, I mean, I look at all of you guys. A couple of you guys have laptops out. Everybody's computer runs something at a different speed, right? But if we say something is big O of n, okay, what we're saying here is we're saying that the worst case number of steps your program is going to take is going to be linear with respect to the size of the input. Okay, so if my computer is 5 times faster than your computer, my computer will probably run it 5 times faster. Okay, but it's still, as the size of the input grows, I'm going to expect a linear speed up in the amount of time it's going to take. Okay, so why is that important? At the bottom of page 1, I have, Big O notation. We are particularly concerned with the scalability of our functions. Okay, so what Big O notation does is it might not predict what's going to be the fastest for really small inputs. For an array size 10, something that you guys know a little bit about graphs, right? We have a graph of x squared, and we have a graph of x cubed, right? There's a portion of time where the graph of x squared is actually bigger than x cubed, right? But then all of a sudden, there's a point where x cubed just goes whoosh, way bigger than x squared. Okay, so if we're in some really small amount of input, Big O notation might not tell us what's the best function. Okay, but Big O notation, we're not concerned about small inputs. We're concerned about really big inputs. We're concerned about filtering the genome. We're concerned about analyzing data from Hubble. Really huge blocks of data. Okay? So if we're looking at a program that analyzes the human genome with 3 million base pairs, some segment that we're looking at, and we have 2 algorithms. One runs in order n time, and one runs in order n cubed time. Okay? What this means is, regardless of the machine that we're running on, so this is algorithm 1, and this is algorithm 2. Regardless of the machine that we're running on, we'd expect algorithm 2 to run approximately n cubed over approximately n squared slower. Okay, so with Big O notation, you can compare 2 algorithms by just looking at the ratio of their Big O runtime. Okay, so if I'm looking at something that has an array of size 2 million as its input, is it clear that this is going to be a much better choice? Okay. So you'll run into that, especially a lot of you guys are taking this for the purposes of scientific computing. So you'll run into Big O notation a lot. It's important to have a grasp of what it means. It's also on the second page of the handout, I have some common ones that you'll see. The first one is constant time. We denote constant time as order 1, okay? But you'll notice that I have here this order 1 is equal to order 10 is equal to order 2 to the 100. Okay, that's unexpected to a lot of people who are learning about Big O notation. Why is this true? That seems kind of ridiculous. This is a really big number. This is a really small number. But yeah. Yeah, exactly. So if we look at a graph of 1 and a graph of 2 to the 100, Okay? We'll see that even though 2 to the 100 is much higher, much bigger than 1, okay? As the size, if this is our input size, as the size of our input grows, do we see any change in these two graphs? No, they're completely linear, or they're completely constant, okay? So anything, when you're doing big O notation, if you run across an algorithm that does not depend on the size of the input, okay, it's always just going to be order 1. Even if it's like, 2 to the 100 steps, if it's a constant number of times, regardless of the size of the input, it's constant time. Other ones you'll see are logarithmic time. Any base for logarithmic time is about the same order. So order log base 2 of n is order log base 10 of n. This is the fastest time bound for search. Hey, does anybody know what type of search we'd be doing in logarithmic time? Something maybe we've, Bisection. Yeah, exactly. Bisection search is logarithmic time, right? Because we take our input, and at every step, we cut it in half, cut it in half, cut it in half, and that's the fastest search we can do. Okay, order n is linear time. Order n log n is the fastest time bound we have for sort. We'll be talking about sort in a couple of weeks. And order n squared is quadratic time. Anything that is order n to some variable, so order n squared, order n cubed, order n fourth, all of that is going to be less than order something to the power of n. Okay, so if we have something that's order 2 to the n, that's ridiculous. That's a computationally very intensive algorithm. Okay, so on page 2, I have some questions for you. 1, 2, 3. Does order 100n squared equal order n squared? Who says yes? All right, very good. How about does order 1/4 n cubed equals order n cubed? Okay. Does order n plus order n equals order n? Okay, yeah. The answer is yes to all of those. And the intuitive sense behind this is that big O notation deals with the limiting behavior of a function. Okay, so I made some nifty graphs for you guys to look at. When we're comparing order 100n squared to order n, 100n squared, n squared, n cubed, and 1/4 n cubed. Okay, what people often think of is what I have here in the first figure. So these are the 4 functions I just mentioned. There's a legend in the top left-hand corner. And the scale of this is up to x equals 80. So you see at this scale, okay, this line right here is 100x squared. Okay, so this is, I think, often a tripping point, is that when people are conceptualizing functions, they're saying, well, yeah, 100x squared is much bigger than x cubed, which is, a lot bigger than 1/4 x cubed, right? So for very small inputs, yes, that's true. But what we're concerned about is the behavior as the input gets very, very large, okay? So now we're looking at a time scale, or a size of up to 1,000. Okay, so now we see here, x cubed, even though it's a little bit smaller than 100x squared in the beginning, all right, it shoots off. Okay, x cubed is much bigger than either of the two x squared, and even 1/4 x cubed is becoming bigger than 100x squared, right, at 1,000. Okay, so that's an intuitive sense why x cubed, no matter what the coefficient is in front of it, is going to dominate any term with x squared in it, because x cubed is just going to go whoosh, real big like that. Okay, and if we go out even further, let's go out to the input size of 50,000. Okay, if we go out to an input size of 50,000, we see that even 100x cubed versus 100x squared versus just x squared, all right, they're about the same. Okay, the x cubed terms now, they're way above the x squared. So the two x squared terms, 100 versus not, just 1, as far as the coefficient goes, they're about the same. Okay, so this is the scale at which we're concerned about when we're talking about big O notation. Okay, the limiting behavior as your input size grows very large. 50,000 is not even that large if you think about the size of the genome, right? I mean, is anybody here bio? Well, it's like the size of like the human genome? How many base pairs? Or even one gene? Or one chromosome? What's this biggest?
It's over 50,000.
Yeah, over 50,000, right? And we're talking about, the amount of data that we get back from like the Hubble Space Telescope. I mean, the resolution on those things are absolutely ridiculous. And you run all sorts of algorithms on those images to try and see if, there's life in the universe. So we're very concerned about the, big long-term behavior of these functions. Okay, how about page 3? One last question. Does order 100 n squared plus 1/4 n cubed equal order n cubed? Who says yes? Yeah, okay. And so I have one more graph. Okay. Down here, these red dots are 100 x squared. All right. These blue circles are 1/4 x cubed. And this line is the sum. Okay? We can see that this line is a little bit bigger than the 1/4 x cubed term. But really, this has no effect this far out. Okay, so that's why we're just going to drop any lower order terms. And whenever you're approached with a big O expression that has a bunch of constant factors and has all sorts of different powers of n and stuff, you're always just going to drop all the constant factors and just pick the biggest thing. Okay, so this line right here is order n cubed. Right. Is that clear to everybody? Okay, so now we've gone through the basics of how we analyze this and why are we looking at this. Let's look at some code. Okay. So the first example. Okay, all of these things right here, in Python, we make the assumption that statements like this, x plus 1, x times y, all these mathematical operations are all constant time. Okay, that's something that you can just assume. Okay, so for this function down here, we have constant time, constant time, constant time, constant time operation. So we'd say this function bar is what? What's its complexity? Yeah, constant time. So the complexity of all of these functions are just O1, okay? Because it doesn't matter how big the input is, right? It's all going to run in constant time. Okay, for this multiplication function here, we use a for loop, okay? Oftentimes when we see for loops that's just going through the input, that's a signal to us that it's going to probably contain a factor of On. Okay, why is that? Okay, right, what do we do in this for loop? We say for I in range y. What does that mean? How many times do we execute that for loop? Yeah, y times. So if y is really small, we execute that for loop just a few number of times. But if y is really large, we execute that for loop a whole bunch of times. Okay? So when we're analyzing this, we see this for loop, and we say, that for loop, all right, must be OY. Okay? Does that make sense to everybody? Okay, good. Let's look at now factorial. All right, can anybody tell me what the complexity of factorial is? Yeah, order n. Why is it order n?
Because it's still a for loop.
Yeah, it's the exact same structure. We have a for loop that's going through range 1 to n plus 1. Okay, so that's dependent on the size of n. So this for loop is order n, and inside the for loop we just do a constant time operation. Right? That's the other thing. Just because we have this for loop doesn't mean that what's inside the for loop is going to, be constant. But in this case, if we have order n times, we do a constant time operation, then this whole chunk of the for loop is order n. Okay, the rest of everything else is just constant time. Okay, so we have constant time plus order n times constant time plus constant time is going to be order n. Okay, how about this one? Factorial 2. Yeah, exactly. This is also order n. The only thing that's different in this code is that we initialize this count variable, and inside the for loop, we also increment this count variable. Okay, but both result times equal num and count plus equal 1, both of these are constant time operations, right? So if we do n times 2 constant time operations, that's still going to be order n. Okay, so the takeaway from these two examples that I'm trying to demonstrate here is a single line of code can generate a pretty complex thing, okay? But a collection of lines of code might still be constant time. Okay, so you have to look at every line of code and consider that. All right, throwing in some conditionals here. Okay, what's the complexity of this guy? Yeah, this one's also linear. What's going on here? We initialize a variable count. That's constant time. All right, we go through character and A string. All right, this is linear in the size of A string, right? Now we say if character equal t. Okay, this character equal t, right? That's also a constant time operation. That's just asking if this one thing equals this other thing. All right, so when we're looking at two characters, we're looking at two numbers, equal or not equal is generally a constant time operation. The exception to this might be equality of certain types. Like if you define a class and you define an equality method in your class and the equality method of your class is not constant time, then this equal check might not be constant time. But on two strings, equal is constant time. Okay? And this is constant time as well. Okay? So linear in the size of A string. Something that's important when you're doing this for exams, it's a good idea to define what n is before you give the complexity bound. So here I'm saying n is equal to the size of A string. So now I can say this function is order n. What I'm saying is that it's linear with respect to the size or the length of A string. Okay? Because sometimes, for, like in the one where there was the input x and y, okay, but the running time was only linear in the size of y. So you'd want to define that n was equal to the size of y to say that it was order n. So always be clear. If it's not clear, be sure to explicitly state what n is equal to. Okay, this code's a little more tricky. What's going on here?
Based on length of A string in the worst case, you have to look through everything in the B string. Oh, if big O is like upper bound, you have to look through the worst case.
Yeah, that was perfect. So just to reiterate, the for loop we know is linear with respect to the size of A string. We have to go through every character in A string. Now the second is if char in B string. Okay? When we're looking at big O notation, we're worried about the worst case complexity, an upper bound. Right? What's the worst case? Yeah, if the character's not in B string, we have to look at every single character in B string before we can return false. Okay, so that is linear. This one single line, if character in B string, that one line is linear with respect to the size of B string. Okay, so how do we analyze the complexity of this? Okay, we have, I want to be able to touch the screen. We have this for loop. This for loop is executed, let's call n is the length of A string. Okay, this for loop is executed n times. Every time we execute this for loop, we execute this inner body. And what's the time bound on the inner body? Well, if we let m equal the length of B string, and we say that this check is order m every time we run it, then we run an order m operation order n times. So the complexity is, we do something of size m n times. Yeah, just order nm. So we execute an order m check order n time. We say this function is order nm. Okay. Does that make sense to everybody? Okay, because you'll see the nested for loops. Nested for loops are very similar to this. Okay, while loops like combine the best of conditionals with the best of for loops, right? Because a while loop has the chance to act like a for loop, but a while loop can also have a conditional. It's actually possible to write a while loop that has a complex conditional that also executes a number of times. And so you can have one single line of code generating like an order n squared complexity. Let's look at factorial 3. Who can tell the complexity of factorial 3? Yeah, it's also linear. It is interesting that factorial is always linear despite its name. We have constant time operations. How many times is the while loop executed? Yeah, n times. And what's inside the body of the while loop? Constant time operations. Okay, so we execute a bunch of constant time operations n times order n. How about this care split example? This one's a little tricky because you're like, well, what's the complexity of len? Okay. In Python, len's actually a constant time operation. This example is very crafted such that all of the operations that are here are constant time. So appending to a list is constant time, and indexing a string is constant time. Okay, so what's the complexity of care split? Constant time?
Is it linear? Because it like depends on the how many times that you're going through the while loop.
Who would agree with constant time? Right, who would say it's linear time? Okay, yeah, very good. It is linear time. That's the correct intuition. Okay, we say, well, the length of the A string is not equal to the length of the result. Okay, these are two constant time operations. Well, what do? We append a value to the result, and then we add up this index. So when is this check going to be equal? This check's going to be equal when the length of the result is equal to the length of A string. And that's only going to happen after we've gone through the entire A string and we've added each of its characters to result. Okay, so this is linear with respect to the size of A string. Something that's important to recognize is that not all string and list operations are constant time. There's a website here that, first off, it says CPython if you go to it. CPython just means Python implemented in C, which is actually what you're running, is CPython. So don't worry about that. There's often two time-bound complexities. It says the amortized time and the worst case time. And so if you're looking for big O notation, you don't want to use the amortized time. You want to use the worst case time. And it's important to note that operations like slicing and copying actually aren't constant time. Okay, if you slice a list or a string, the complexity of that operation is going to depend on how big your slice is. Okay, does that make sense? Because the way that a slice works is it walks through the list until it gets to the index, and then keeps walking until the final index, and then copies that and returns it to you. Okay, so slicing is not constant time. Copying is similarly not constant time. Okay. For this little snippet of code, all right, this is just similar to what we, oh yeah.
For the last one, if you have something that depends on, let's say, a string in this case, with the big O, do you write O and then the length of the string, or you can just do O, big string?
So this is what I was saying. You want to define what n is. So we'd say something like n equals the length of A string. And then you can say it's order n. Okay, right? It's important to define what you're saying the complexity is related to. Okay? So here I'm saying if we let n equal to the size of z, can anybody tell me what the complexity of this snippet of code is? Pardon me? Yeah, precisely, order n squared. Why? Well, because we execute this for I for loop here, okay, order n times. Each time through this for loop, the body of this for loop is in fact another for loop, all right? So my approach to problems like this is to step back a minute, all right, and ignore the outer loop. All right, just concentrate on the inner loop. What's the runtime of this inner loop? Yeah, this is order n. We go through this. Now go to the outer loop. All right, just ignore the body. Since we've already analyzed the body, ignore it. What's the complexity of the outer loop? Also order n. So now you can combine the analysis. You can say, for order n times, I execute this body. This body takes order n times. So if I execute something that's order n times, that is order n squared complexity. Okay, so we just multiply how long it takes the outer body of the loop to take the inner body of the loop. And so in this fashion, I could give you now probably a 4 or 5 nested for loop, and you could tell me the complexity of it, right? Harder sometimes to understand is recursion. I don't know how important it is to understand this because I've never actually taught this class before, but Mitch did tell me to go over this, so I'd like to touch on it. So consider recursive factorial. What's the time complexity of this? How can we figure out the time complexity of a recursive function? Right? The way we want to figure out the time complexity of a recursive function is just to figure out how many times we're executing said recursive function. Okay? So here I have recursive factorial of n. Okay? When I make a call to this, what do? Okay? I make a call to recursive factorial n minus 1. All right? And then what does this do? This calls recursive factorial on a subproblem of size n minus 2. Okay? So oftentimes when you're dealing with recursive problems, to figure out the complexity, what you need to do is you need to figure out how many times you're going to make a recursive call before a result is returned. Okay? Intuitively, we can start to see a pattern. We can say, I call it on n, and then n minus 1, and then n minus 2, and I keep calling recursive factorial, all right, until n is less than or equal to 0. Okay? When is n going to be less than or equal to 0? Well, when I get n minus n. All right? So how many calls is that? Yeah, this is n calls. Okay, so it's a good practice to get into being able to draw this out and work yourself through how many times you're running the recursion. Okay, and when we see we're making n calls, we can say, oh, this must be linear in time. Okay? How about this one, this foo function? Right. This one's a little harder to see. Okay, but what are we doing? Right? We call foo on input of size n, right? Which then makes a call to a subproblem of size n over 2, which makes a call to a subproblem of size n over 4. And so on until we make a call to subproblem of some size. Okay, so this is n. This is 2 to the first. This is 2 squared. All right, we start to see a pattern. 2 squared, 2 cubed, 2 to the fourth. All right, so we're going to keep making calls on a smaller and smaller and smaller subproblem size. But instead of being linear like before, okay, we're decreasing at an exponential rate. Okay? There's a bunch of different ways to try and work this out in your head. I wrote up one possible description. But it's when we're decreasing at this exponential rate, what's going to end up happening is that this recursive problem where we make a recursive call in the form to a subproblem of size n over b, all right, the complexity of that is always going to be log base b of n. Okay, so this is just like bisection search. Okay, where bisection search, we essentially do in bisection search, we restrict the problem size by half every time, and that leads to logarithmic time, actually log base 2 of n. This problem is also log base 2 of n. If we change this recursive call from n over 2 to n over 6, we get a time complexity of log base 6 of n. Okay? So try and work that through. You can read this closer later. Definitely ask me if you need more help on that one. All right, the last one is, how do we deal with time complexity of something like Fibonacci? Okay, Fibonacci, fib n minus 1 plus fib n minus 2. Initially, that kind of looks linear, right? We just went over the recursive factorial, and it made the call to a subproblem of size n minus 1. And that was linear, right? Fibonacci is a little bit different. If you actually draw it out in a tree, you start to see, like, at every level of the tree, we expand the call by 2. Okay, now imagine this is just for a Fibonacci of 6. And whenever you're doing big O complexity, you want to imagine an input of 100, 1,000, 50,000. And you can imagine how big that tree grows. Okay? Intuitively, the point to see here is that there are going to be about n levels. All right? To get down to down to 1 from your initial input of 6. Okay, so to get down to 1 from an initial input of size n is going to take about n levels. Right? The branching factor of this tree at each level is 2. Okay, so if we have n levels, and at each level we increase our branching factor by another 2, we can say that a loose bound on the complexity of this is actually 2 to the n. Hey, this is something that's even less intuitive, I think, than what we did before with the logarithms. So try and work through it again, play with it a little bit. There's actually a tighter bound on this, which is like 1.62 to the n, which is a lot more complicated math that you can look up. But for the purposes of this class, it's sufficient to say that Fibonacci is order 2 to the n. Okay. So does that roughly clear up some time complexity stuff for you guys? Okay, awesome. Does anybody have the time? I forgot my watch today. 12:42. Okay, excellent. That gives us a little bit of time to talk about object-oriented programming. Does anybody have any specific questions about object-oriented programming? No? Okay, how about this? How many of you guys finished the problem set and turned it in already? Or did any of you guys not turn in the problem set yet? Or I'll talk loosely about it then, but not too specifically. And anybody have any questions from, I guess, at least the first part? You know, we're making some classes, making some trigger classes. Yeah?
What's the importance of having like self.get with equal to get? Like, why do you have to use it?
Self dot what?
Like, if you like wanna, so in the first part we were.
When we have like the self, we have like the getter methods. Yeah. Okay, so what's important about that? I'll tell you what's important about that. So we have a class. Let's say we have a class person. Okay, so we define our init method to just take a name. All right? And so now, what the problem set asked you to do was to define a getter method. All right? Define a getter method called getName. That just returns the attribute. Okay, so what's the point of this? Okay, because I can just say Sally equals person . Okay, so here I define a person named Sally, and you know, I initialize a person with the string Sally. All right? And if I just look at Sally.name, that's going to just directly print the attribute. Okay, so why did we need this getName function? Like, what's the point of this additional getter method? And does anybody know why that is? Right, so that's what it does. This getName does return the attribute name. But we don't need this method to just look at the attribute name. All right? Here. Let's actually code this up. so we have class person. Okay, so if we run this code, right, and over here in the shell, we define Sally equals person with the name Sally. Okay? If I just print Sally.name, it prints the attribute. So why did I need to provide this getter method called getName that does the same thing? That's the question, right? Like that seems sort of redundant, okay? But there's actually a pretty big important reason for it. Let's say we set sname equal to the attribute Sally.name. All right? If we look at sname, we see Sally. And but now if I say, actually I'm not sure if this is the correct reasoning. Okay, this is not the proper. This is going to be better. All right, let's say Sally equals a person, Sally, who's taking what? 1803, 600, and 511. Okay? So now I can look at the attribute classes to show Sally's classes, which are weird floats. And I can also use Sally.getClasses to look at Sally's classes. Okay? If I set a variable s_classes equal to Sally.classes, okay, this binds this variable s_classes to the attribute Sally.classes. Now if I say s_classes.append 1401, all right, if I now look at the attribute Sally.classes, it now has 1401 in it. Okay, this is not safe. This is not type safe. Okay, because the reason for that is if you define a class and you access the class's attributes directly instead of through a getter method, you can then do this, and sometimes it's accidental. All right, you'll set some variable equal to some attribute of a class. Then later on in your code, you'll alter that variable. Okay, but that variable is not a copy of the attribute. Okay, yes, you can make copies of the attribute and stuff, but the overall takeaway is that in programming, we try to do something called defensive programming. Okay, this isn't defensive because it is possible, if you code it incorrectly, to alter the attribute of the class, or the instance of the class. But if we use the getter method, if instead of Sally.classes, instead of directly accessing the attribute here, we had set s_classes equal to Sally.getClasses, and then we had changed s_classes around, okay, that wouldn't have happened. Because the getter method, it does return self.classes, but in the way that Python is scoped, and when we return something, we're not returning the exact same thing. The reference that we're returning a copy of it. Okay, does that make sense? All right, cool. Other questions about classes? I mean, we have a little class up here. If there's like some basic stuff that you'd like explained again, now's the time.
What's the difference between, in this case, s_classes and Sally.classes?
So here I'm setting just some variable s_classes equal to the attribute Sally.classes. It's just like setting, you know, any sort of variable equal to some other quantity.
So you appended the variable, but it also appended like the attribute of Sally.
So what I did here was I set the variable s_classes equal to this attribute Sally.classes. And then because I know this is a list, I appended another value to it. Okay, but this is the same as when we have two lists. If we have a list called A and we say A is equal to 1, 2, 3, and I say B is equal to A. Okay, what is B? Now if I say B dot append 1401, what does B look like? What does A look like? Right, because they're aliases of each other. So what I did here, when I set S classes directly equal to the attribute Sally.classes, I made S classes an alias of the attribute. Okay, but the problem with that is that then I can change them, and because they're aliases, the attribute itself is changed. Okay, and we don't want to do that in object-oriented programming. When you define an object, the only way you should be able to change an attribute is through some method of the class that allows you to change that attribute. Okay? So if I wanted to be able to add a class to Sally's class lists, I should define a method called define add classes, or define add class that does self.classes.append new class. Okay? While technically it's possible to directly access an attribute, it's really bad practice to do so, simply because this unexpected behavior can result. And also because if you say, oh, well, it's not going to matter for this one time, I'll remember how to do the right thing. The problem with that is it's often the case that you're not the only person using your code. Okay? So it's a better practice to provide all the sorts of methods that you would need to do with the class in order to get and access and change attributes as methods within the class. Okay, does that make sense? Okay. So yeah, this is maybe our one violation if you guys have been attending my recitation, our mantra of programmers are lazy. This is less lazy than just directly accessing the attributes. But even though we know that programmers are super, super lazy, programmers also like to be super, super safe. So when there's a trade-off between defensive programming and being lazy, always pick defensive programming.